In this session, let us discuss the TE or TM mode analysis in the cavity resonators. So, last session we have discussed about the propagating modes in the circular waveguides. Also, we have discussed the cavity resonators, what are the cavity resonators and the resonant frequency. And now we are going to see the mode analysis, that is how the TE wave or TM mode changes for a cavity resonator. What is the difference between the TE mode representation in waveguide, circular waveguide and circular cavity resonator. Similarly, what is the mode difference representation in rectangular waveguide and rectangular cavity resonator, that you can be able to identify in this session. So, myself Dr. V. Vijayasri Bolissetti, Associate Professor, Department of Electronics and Communication Engineering, and today we are going to discuss the cavity resonators, that is TE or TM mode analysis. So, what is the outcome of this session? At the end of this session, the student will be able to analyze the different modes that are propagating through the rectangular cavity resonator as well as the circular cavity resonator, and also can identify what is the dominant mode and the degenerate mode in the rectangular cavity resonators. So, first let us see the TM wave in a rectangular waveguide. So, what is a TM wave? TM represents transverse magnetic wave. That means transverse magnetic means whose Hz component is 0, and we can define the Ez. So, what is the Ez? For a rectangular cavity, we have defined that Ez is equal to some C sin m pi by a x sin n pi by b y e power j omega t minus gamma z. So, if the propagation direction changes, this may be plus z or minus z. So, generally gamma for propagation, it should be alpha should be 0 and that should be equal to j beta. So, as the propagation direction may be towards positive z direction or negative z direction, we can write this gamma as plus or minus j beta for the propagation. Okay. So, as the wave propagates along the cavity resonator, along the walls in the cavity resonator, it moves back and forth. That means, if one sometimes it is moving, for example, if you consider a rectangular okay. So, sometimes while it is in the forward direction, the wave moves in this direction, and when it reflects back, the wave is moving in this direction. So, sometimes it is moving in the positive z direction or sometimes it is moving in the negative z direction. So, it may be changing, that means, so it can be written as a plus or minus. Okay. So, now if the wave is propagating, then the condition for the propagation is gamma is equal to plus or minus j beta, gamma is equal to j beta. So, let us substitute this gamma in equation 1. So, when we substitute this 2 in 1, we get Ez is equal to C sin m pi by a x sin n pi by b y e power j omega t plus or minus j beta z, or simply we can also write it as e power j omega t plus or minus beta z. Okay. So, now we can expand what is or this term is a combination of two terms, that is e power j omega t and e power j beta z. Okay. So, we can also split it as e power j omega t into e power plus or minus j beta z. That means, it is a form of e power j omega t plus j beta z or e power j omega t minus j beta z. Okay. So, let us expand this e power j beta z by considering the different amplitude constants for onward and backward movements. So, let us consider A plus is the amplitude constant for when it is moving forward, and A minus is the amplitude constant when it is moving backward. For the reflected signal we consider A minus is the amplitude, and for the forward signal let us consider A plus is the amplitude constant. So we are going to represent this e power plus or minus j beta z as, when it is moving in this forward direction, it is A plus e power minus j beta z, and when it is moving in the backward direction, this is backward direction and this is forward direction, and so when it is moving in the backward direction, the amplitude is A minus e power plus j beta z into c sin m pi by a x sin n pi by b y e power j omega t. So here, while if you go for the boundary conditions, if you apply the boundary conditions, then we can say that the boundary condition is Ez is equal to 0, at Z is equal to 0 and Z is equal to D, and as we are going with the Tm, then we can also consider it as a field expressions that Ey is equal to 0, or the derivative of this function should be equal to 0. So this can happen only if this, this is if Z is equal to 0, at Z is equal to 0 and at Z is equal to D, we get Ez is equal to 0 if only A plus and A minus are equal at this moment. Okay. So by taking this A plus and A minus are same, that means we are having the same coefficient for this e power j beta z and e power minus j beta z. So simply we can also write this A plus is equal to A minus is equal to some A, a common constant A. So now if you take this A as common, then we are going to get e power minus j beta z plus e power j beta z. Simply it is like e power j theta plus e power minus j theta, so we can write it as 2 cos theta. Okay. So by just applying the trigonometric relations, by expanding this exponential term, we can write simply this term as 2 cos beta z c sin m pi by a x sin n pi by b y e power j omega t. So here we have some arbitrary constants, a, 2 and c. So all these arbitrary constants together we can write as a simple single arbitrary constant c, and cos beta z, where we have derived what is beta. Beta, we know that beta is equal to p pi by d, so we substitute beta is equal to p pi by d z sin m pi by a x sin n pi by b y e power j omega t. So this is our relation for Ez, and so this is what we have obtained for Tm wave, and similarly for TE wave, Ez is equal to 0 and we have an expression for Hz. Okay. So let us start from this, that as Ez is equal to 0 for TE wave and Hz is equal to c cos m pi by a x cos n pi by b y e power j omega t minus gamma z. Okay. So now let us substitute what is gamma here. For propagation through the waveguide or a cavity resonator, this gamma should be equal to j beta. It may be in the positive or negative z direction, so we can take gamma is equal to plus or minus j beta, because always the wave propagates back and forth in the cavity resonator. We can take gamma is equal to plus or minus j beta, and if we substitute this in 1, we are going to get Hz is equal to some c cos m pi by a x cos n pi by b y e power j omega t plus or minus j beta z. Here also we consider there is a different amplitude constants for while moving in the positive z direction and in the negative z direction. So let us consider A plus be the amplitude constant while moving in the forward direction, and A minus is the coefficient amplitude constant in the while moving in the backward direction, reflected signal. Okay. Now, so from this we get what is Hz, and Hz is a combination of A plus e power minus j beta z plus A minus e power j beta z c cos m pi by a x cos n pi by b y e power j omega t. And in this, when we apply the boundary conditions, that is the boundary conditions here is that Ey should be equal to 0 at z is equal to 0 and also at z is equal to d. So, this happens only when a plus is equal to minus a minus, okay, a plus is equal to minus a minus. That means, if we take a plus is equal to a, then a minus is equal to minus a, okay. So, let us substitute this a plus is equal to a and a minus is equal to minus a, then we are going to get the relation for hz, and if you take a as common, you will get e power minus j beta z minus e power j beta z c cos m pi by a x cos n pi by b y e power j omega t. But e power j theta minus e power j theta, we can write it as a 2j sine, but here it is in reverse direction. So, we can say that it as minus 2j sine beta z minus 2j sine beta z a c cos m pi by a x cos n pi by b y e power j omega t. So, this minus a 2j c minus a 2j and c together we can write it as a single arbitrary constant c, then we write sin beta z where beta is equal to p pi by d. So, p pi by dz cos m pi by a x cos n pi by b y e power j omega t. So, this is the expression for hz. So, for while discussing the Tm, we got Ez is some c cos p pi by dz sin m pi by a x sin n pi by b by e power j omega t, and while discussing the Tm, we get hz is equal to c sin p pi by dz cos m pi by a x cos n pi by b by e power j omega t. So, we got the wave equations for Te and Tm, and if we observe that this is the Tm wave Te wave equation which is having the terms m, n and p, where m, n, p all are integers. So, this wave we can simply call it as Te m n p, just wait, Te m n p, and previously we have obtained the transverse magnetic. So, the Tm also, it is also represented as with the suffix same Tm m n p. Okay. So, now let us see the Te wave in the circular cavity also. So, in the last session we have discussed what is the Te wave in the circular cavity, circular waveguide, and so we start from the Te wave in the circular waveguide and apply the boundary condition for the circular cavity, because here the boundary condition is, that means we are going to place a shorting plate after a particular distance d. So, we are applying that boundary condition on the direction, suppose if you say z, at z is equal to d, we are going to place a shorting plate. So, previously while discussing the waveguides, we have taken the x dimensions and y dimensions, because we have a waveguide with a on x and y, but now when we come for the cavities, we have a dimension along the z direction also. So, we are applying the third boundary condition onto the already applied boundaries. Okay. So, now let us see the Te wave in the circular waveguide. So, we know that the Te wave means Ez component is 0 and Hz is defined as some C naught Jn of rho h cos n phi e power j omega t minus gamma z. So, this Jn of rho h is going to represent the nth order Bessel's function, okay, where rho h, these coefficients are rho is going to represent the coefficient rho phi and z are the coefficients of the cylindrical coordinate and coordinate system. So, rho means generally is going to represent with the radius of the circular cavity, okay, and phi is the azimuthal angle at which the wave is going to propagate along this z direction. Okay, anyhow, so whether it is a circular cavity or it is a rectangular cavity or it is a waveguide, whatever it may be, for the wave propagation always alpha should be equal to 0. That means there should not be any attenuation. Then obviously this gamma should be equal to j beta. Gamma should be equal to j beta. So this gamma should be equal to plus or minus j beta, because as we are placing a shorting plate at a distance of d, that means suppose if you take a circular waveguide like this, so this circular waveguide, this is a shorting plate and this is a shorting plate, and the distance between these two is d. So suppose if the wave is propagating along this direction, that means z is equal to d. It starts at z is equal to 0 and it winds up at z is equal to d. So these are the boundaries that we have to substitute, and so it may be propagating that by hitting the shorting plates, the wave may be propagating in the both the forward or in the reverse direction. So it is moving back and forth, and the propagation takes place only at alpha is equal to 0. So we substitute this gamma is equal to plus or minus j beta. Okay, and when we substitute gamma is equal to j beta in equation 1, then this can be written as C naught j n rho h cos n phi e power j omega t plus or minus j beta z. Here also we consider, as while it is moving in forward direction, its constant is amplitude constant is a plus, and while moving in the backward direction, let us consider its amplitude constant is a minus, and expand e power j beta z plus or minus j beta z as a plus e power minus j beta z and a minus e power j beta z. So if we expand this, we get a plus e power minus j beta z plus a minus e power j beta z c naught j n rho h cos n phi e power j omega t. And here we have this e power minus j beta z, e power j beta z. We need to apply the boundary condition for this to solve these arbitrary constants. So let us apply the boundary condition. Again, as it is a TE wave, the boundary condition is Ey is equal to 0 at z is equal to 0 and z is equal to d. Here also we have considered the distance that at which we have placed the shorting plates, the distance is d. So at z is equal to 0 and z is equal to d, this Ey is equal to 0, and for this, as the Ey has to be 0, the condition is a plus should be equal to minus a minus. So a plus, if it is equal to a, then a minus is equal to minus a. Let us substitute this in equation 14, and so if you take this a as common, you will get e power minus j beta z minus e power j beta z c naught j n rho h cos n phi e power j omega t. And of course here you can see what is h, because this is the TE mode that is propagating. So we can also write this h is equal to, for TE mode we can write it as by a, PNM dash by a. So this is the h here, we can substitute that h also in this Jn. Anyhow, by simplifying this, we are going to get it as minus 2j sin beta z. So we will get minus 2j sin beta z. So this is minus a, 2j and c naught, altogether constants. We can write it as a single arbitrary constant, that is c naught, and sin beta can be written as p pi by d and j n rho h cos n phi e power j omega t. So this is actually the TE wave equation in the circular cavity, and in this the TE wave, how it is represented is, unlike in the rectangular cavity, it is represented as NMP. In the rectangular cavity, it is represented as MNP, but whereas in the circular cavity, the general notation of representation is NMP. Okay, so NMP. Okay, now let us see what is the transverse magnetic wave representation in the circular cavity. For this, Hz is equal to 0 and we define Ez, where Ez is equal to C naught Jn dash rho h cos n phi e power j omega t minus gamma z. And as it is a circular cavity, the boundary conditions here also same, z is equal to 0 and z is equal to d, and the condition for propagation should be gamma is equal to plus or minus j beta, and also we can take a different coefficients for propagating along the in the forward direction and the backward direction. So if we take the propagation along the forward and backward direction is a plus and a minus, then simply we can write this e power plus or minus j beta z in terms of a plus and a minus coefficients. Okay, so the Hz is equal to a plus e power minus j beta z plus a minus e power j beta z. So we are discussing here TM waves that are propagating. So let me correct here, this is not Hz, it should be Ez, because Hz is equal to 0. So Ez is equal to a plus e power minus j beta z plus a minus e power j beta z c naught j n dash rho phi rho h cos n phi e power j omega t. Now if you apply the boundary conditions, that is Ez is equal to 0 at z is equal to 0 and z is equal to d, then a plus and a minus are equal, and I am taking this both are same. So a plus is equal to a minus is equal to a, and if we substitute this a in place of a plus and a minus, then we are going to get e power minus j beta z plus e power j beta z c naught j n dash rho phi cos n phi e power j omega t. Now it is this can be written it as a 2 cos beta z. So we get these two are arbitrary constants, all this together we can write it as a single arbitrary constant, that is c naught j n dash rho h cos n phi and cos beta z, beta can be written it as cos p pi by dz e power j omega t. Okay, so this is the expression for Tm, and hence the general Tm expression can also be represented as a Tm NMP. Tm NMP. For circular we represent NMP, and for rectangular we represent MNP. So identify this notation properly, and so now let us define what is the dominant mode. So before going to this dominant mode, so far we have discussed about the TE mode and TM mode equations in both rectangular cavity and circular cavity. So we have already taken the TE wave equation in a rectangular waveguide. After simplifying the boundary conditions, whatever the signal we got, for that now we are applying another boundary condition, that while the wave is propagating from z is equal to 0 to z is equal to d, or while it is reflected back from z is equal to d to z is equal to 0. So we have applied the boundary conditions and we have obtained the TE and TM wave equations in both the rectangular and circular cavity. Now let us see how we are defining the dominant mode. So as we have seen in the introduction slides of the circular waveguides and all, we have defined that the dominant mode means the mode which have the low resonant frequency or the least resonant frequency. We call it as the dominant mode. So we have defined the resonant frequency, but the resonant frequency for the rectangular waveguide and the resonant frequency for the circular waveguide are differ. Also the resonant frequency for the rectangular waveguide is same for both TE and TM, and for circular waveguide it is differ for TE and TM. So let us see separately for a rectangular waveguide and for a circular waveguide. So let us see the expression for the resonant frequency. So this is the expression for the resonant frequency in a rectangular waveguide. So in this expression, if we have to get f naught to be minimum, what should be the condition? If you consider this f naught is a function of a, b, d. Of course, the mode may be either TEMNP or TMMNP. I will write here. The mode that is propagating through the rectangular cavity may be represented as TEMNP or TMMNP, and always m corresponds to the dimension A, n corresponds to the dimension B, and d corresponds to the d dimension corresponds to the integer p. Okay. So that means if suppose A, B, D are all in the denominator, and generally A is the broader dimension of the rectangular waveguide. If we take the rectangular waveguide like this, this is the rectangular cavity resonator. So this is the broader dimension of the rectangular waveguide A, and this is B for the front face, and this dimension is D, depth of the cavity resonator, and the general